We will solve some problems today that involve imagining a new graph and running Dijkstra on them. I've already made a tutorial on them. Unless you are familiar with these types of problems, you should probably watch that first, or else everything else we see won't make any sense. This is problem 1, you have enough time to pause and read it. This is problem 2 if you want to pause and read it. And of course, this is problem number 3 if you want to pause and read it. Now we'll be looking at CPP implementation. Let's start implementing problem number 1. The first thing we're going to need to do is we're going to need to read our big parameters, the number of nodes and the number of edges, n and m. Okay. Then we're going to need to read each edge individually. So for each edge, we have this basic for loop, and for each one we have 3 integers, b, a, and dist, and it means that node A will connect to node B with a distance of dist. And we do it like this, we read them, and we're going to create a function, make edges, A, B, and dist. Like this. We'll implement that function later because it's going to be different for each problem. As a reminder, we will be storing each edge in std vectors. We have v for the name of the neighbors and d for the distances to our neighbors. For those of you that don't remember, v and d are vectors. So basically these are two-dimensional arrays where the second dimension has a dynamic size. This is what these are. And the size for the first dimension is the maximum value of n. We do them statically and globally like this so that it performs better. And max n is 2 times 10,000. Always add a bit extra. It reduces the chance that you go out of bounds if you make a mistake and doesn't make anything harder for you. It's free not to do it. So we're gonna make a function, connect, int a, int b, int dist, to create edges, and it's very simple. v of a dot push underscore back b, and d of a dot push underscore back dist. If you've watched the previous video, the format we use is the same. So this means for the vector of node number a, this vector where it stores the neighbors, add the neighbor b, and for the distance array, add dist. The next part is adding this weird characteristic of our graph where we have multiple node 1s and multiple node 0s, etc. So we're going to create a function and it's going to take I, and I will be 0, 1, 2, 3, etc. And we're gonna also say, let's say bit. And the bit will be either 0 or 1. If bit is 0, this means that we haven't used the orb yet. And if bit equals 1, we have used the orb. All we have to do is make sure we don't get any collisions by combining these numbers. And the way we do this is to just return I times 2 plus bit. And that's all it takes to make this encoding function. Now on to creating the make edges function, int a, int b, int dist. So to make edges we have to connect encode of a, 0 with encode b, 0 with a distance of dist. So what this means, if it's a is 0 and b is 1, it would make this edge here. Encode a of 0 would be this one, and code b of 0 would be this one. Likewise, we connect encode of a, 1 with encode of b, comma 1 with a distance of dist, which would be, in our case, the ability to travel from 0x to 1x, because this is our coding format. And to travel between them, we just add connect in code of a comma 0 with in code b comma 1 with a distance of 0. These are the purple edges. The graph is done. Now all we have to do is run Dijkstra. The first thing we do is we copy paste Dijkstra's algorithm we wrote from the previous episode. It's exactly the same as you remember. It takes 4 parameters. V, we have that. D, we have that. It needs an array where it will store the answers, and everything to start with -1 or infinity will do that. And the starting node. I made a video on this. I'm not gonna tire you with that again. So we're going to need to create an answer array, once again of size max n. Then, to run the algorithm, we need to set everything to 0. So it's ans, -1, size of ans. Then we just have to run Dijkstra. Oh, by the way, I need to add an S here, because I don't know how to spell Dijkstra of V, D, ans, and what's our starting node? Well, it's in code of 0, 0. That's it. And that will calculate the shortest paths. Then we just have to print it, the one we want. So, like this. And which one do we want? We want the answer of in code of ni -1, 1. That's the one we want. And that's it. Alright, I compiled it on this graph and this graph, and it seems to work fine. Now moving on to problem 2. To show you how similar they are to problem 1, we're just going to be making adjustments to the code for problem 1. So the first thing we do is we read J and C, the number of ninjas and the number of crowbars. Then we have to see where we have ninjas. For that, we're going to create an array of bool, call it has ninja, of size max n. Now, max n goes to 2 times 10,000, and the number of ninjas goes up to 10,000. So we are wasting half our memory, but that's fine, we don't really mind that. Next up, we have to read them. So we're gonna have to create a for loop for int I equals 0, I smaller than j, plus plus I. And we're going to create a temporary variable, and it's going to store where the ninja is. So this means that temp has a ninja on it. So has a ninja of temp will become true. As a reminder, because this is a global array, everything starts as false, so we don't have to initialize the other ones as false. Moving on, let's start making the graph now. Our encoding function will be the same. It just takes an integer and a bit and creates a unique integer out of them. But what the bit means just changes. If the bit is 0, that means that we don't have a crowbar. And if the bit is 1, it means that we have a crowbar. That's all. So the function is pretty much the same. For make edges, we get rid of this last part with the free edges. That was a unique part of the first problem. And then, look at that. We have the part of the graph where we don't have a crowbar and the part of the graph where we do have a crowbar. The only unique thing here is that for the first part of the graph, we don't make an edge if we have a ninja. So we have to make this check. If not has ninja of A, and also not has ninja of B. Okay, this means that now we can make the connection. Next thing, we have to read where we have crowbars. So we'll go back down. For int I equals 0, I smaller than c, plus plus I. We're gonna do the same thing we did with the ninjas. We're going to read a temporary variable, and this means that temp has a crowbar. How do we represent that in our graph? We just need to create these purple edges. So connect encode of temp comma 0 with encode of temp comma 1, and the distance is 0. So from this part, 3 comma 0 would be this guy, and 3 comma 1 would be this guy, for example, for crowbar on 3. Now our graph is complete, and Dijkstra is also complete. It's the same as before, we don't make changes to Dijkstra. Now we have the shortest path between this guy and every node in the graph, but unlike the last problem, we don't know which of the final nodes is the one responsible for the answer. So we're going to create 3 integers, ans1, or ans0 probably is better, ans1, and final ans, and the first answer is going to be, of course, the ans of encode the last node, which is n-1, comma 0, and the second answer is going to be ans of encode the final node once again, comma 1. And of course, the final answer of both of them is going to be the minimum of those. So ans std min, ans 0, comma ans 1. So this is the one that we want to print, the final answer. Final answer. I run it on this simple graph and it works fine, so on to the next one. Moving on to problem 3. The first thing we're going to need to do is increase the size of max n. This is because if we look at the graph we'll make, it's actually triple the number of nodes, and we gave the same restriction with n. Then of course we are no longer dealing with ninjas, so we'll get rid of this line. Now moving on to encode, something interesting happens, because this time our secondary information can take 3 values. So it's no longer bit, let's just call it v. So what we'll do is we will multiply I by 3, and we get the same results. So if v equals 0, we will say that we don't have a vehicle. If v equals 1, we have a unicycle. Let's do it here. V equals 1, a unicycle. And v equals 2 means we have a scooter. Okay. And for the same reason, we just don't want collisions, and multiplying by 3 does that. On to making edges, we remove the stuff with ninjas and align this better. So, for the no vehicle part of the graph, we're all good. So the distances are the same. Now we just have to check if the distance is odd or even for the unicycle and the scooter part of the graph. So, if distance modulo 2 equals 0, so if our distance is even, then the unicycle graph will be halved. So we go here, and for the first one is divided by 2. And we're going to connect encode of a, comma 2 with encode of b, comma 2, and the distance this time will be the same. Otherwise, if we're working with an odd number, then we're going to connect encode a, comma 1, scooter part of the graph, sorry, unicycle part of the graph is what we're doing now, and distance will be the same, and for the scooter part of the graph, this is it. A little side quest I want to give you guys, if you can tell me your answers in the comments, is doing this without if-else statements. You can actually do it with a bit of bit magic, and it's faster, it also takes less lines, potentially. I can give you my answer, but I wanna hear your ones first. So this is it with making edges and encoding. The other part of the graph we need to add is this ability to travel between no vehicles, unicycles, and scooters. And we're gonna do that by reading where we have unicycles and where we have scooters. So we're gonna largely reuse this section here. We're gonna change the variable names though to make them more appropriate to this problem. So instead of reading ninjas and crowbars, we read unicycles and scooters. Unicycle and scooter. Now, what do we do when we see that temp has a unicycle? Let's move to the right. Well, if your node 1 has a if node 4 has a unicycle, then it means we connect node 4 with a v of 0 and node 4 with the extra information of 2 to the one with 1. So we're just gonna do connect of encode of temp, 0 to encode of temp, 1 with a distance of 0. And we're gonna do the same encode temp, 0 with encode, temp, 2, encode of temp, 1 with a distance of 0. And we're gonna do the same with our scooter. So let's do the same with the scooter. The target is number 2, and we'll do it from 2 and 1. With these things, the graph is completed. Dijkstra's algorithm is always the same, but this time we have 3 answers we need to compare. So we're gonna do ans2, add this one, and ans2 equals ans of encode last node, which is n-1, 2. Okay, and final ans equals std mean final ans, ans2. With that, we're done. Before we compile, there's a little trick I want to show you guys. Maybe if you're working with a larger project, obviously this is a very small program, maybe you'll get forgetful or confused about what these values should be whenever you're trying to encode what is 1. It means no vehicle. What is 1? It means unicycle, and you just get confused with these things. In this case, a good thing you can do is you can do const expression and int, and then you can say, for example, no vehicle equals 0. And now, instead of writing 0 every time, and maybe you forget what that means, you could just write no vehicle, and it would work fine. And of course, you can do const expression for unicycle and scooter, and this way, instead of just using numbers that you forget what they mean, you can use words. But obviously, for here, it's kind of irrelevant. And I ran it on this example. It works fine. That's all I have for today. I hope you enjoyed it. I hope you learned something. Thanks for watching. I couldn't resist myself. I want to show you the bit magic that I figured out for calculating the edges. This is your last chance to pause right now if you want to figure it out yourself. I'm gonna show it now. Ta-da! This is the monstrosity. So we calculate if it's odd and if it's even. And then we use shifting. So if is even is 0, this does nothing. If it's 1, it divides by 2. And this is performs better, is more elegant than using an if or an else.